I'm now going to add about a milliliter of 10 molar sodium hydroxide. Based upon the amount of copper that can possibly be in solution, this should be in significant excess. Now, whenever we do this particular reaction, what you get out of it depends a lot on conditions of the reaction that are somewhat difficult to control. If your sodium hydroxide solution has been very, very freshly prepared from water which was distilled a day ago, and sodium hydroxide that's very, very pure, then your precipitate will probably be an extremely deep blue and very, very jelly-like. To the extent that that sodium hydroxide solution has been sitting around for a while, you probably get something which is more like this. It's going to have various different colorations, so there could be some greenishness to it. And it's also probably going to have a more light blue cast. The reason is that sodium hydroxide solutions that sit around for a while, particularly if they're very concentrated, like 10 molar sodium hydroxide, will have a tendency to absorb carbon dioxide from the atmosphere. So carbon dioxide from the atmosphere reacts with the sodium hydroxide to form bicarbonate and carbonate ions. And this is a precipitation reaction, right, with the hydroxide, but it's also potentially a precipitation reaction with bicarbonate and with carbonate ions. None of those are soluble with copper. And when they get mixed together, there's a competition. A lot of times when you do a reaction like this, when you take a concentrated hydroxide solution and a precipitating ion and you mix the two of them together, what you're going to get is a complicated mixture. We would write a balanced chemical equation for this based upon just the hydroxide part, but we also have to sort of keep in mind that it's often the case that there's going to be carbonates and bicarbonates precipitating out at the same time. And so really what we need to know at this point is if we're going to move on to a new stage of this reaction, we need to figure out some way of getting all of the different possibilities for products in our particular reaction, but also for products, in any reaction in the room. How do we get everybody to the same point, right? So that we can move on to the next step. I have placed the test tube into a 50 milliliter beaker that has a little bit of water in it, and there's a very small piece of paper clip at the bottom of that 50 milliliter beaker that's acting as a stir bar for that water. The hot plate's on, so we are going to be heating the water up around the test tube. In this particular case, I'm using as little water as possible, primarily because the heat capacity of water is very high. I don't particularly feel like sitting around waiting for the water to boil, considering that's not actually part of the chemical reaction. So, since the purpose of the water is entirely to moderate the temperature to get the heat to the test tube as quickly as possible and as evenly as possible, I'm going to only use the minimal amount of water that's necessary. one of the things that you should be able to see is that, you know, clearly the bottom part where the water is next to the test tube, we see that there has been some kind of change in color very dramatically. And in the top part of the test tube, where the material hasn't yet got to that temperature, we still have the same sort of blue color. And so now this is where I will take my my pipette and just churn that in there a little bit. So again, this is to ensure that this material all gets to the same place. At this point, when we move into the next step of the reaction, we're going to be exposing the chemical reaction to an acidic solution. We've added an excess of base, and so we would like to try to get rid of as much of that excess base as possible. In other reaction sort of procedures, what you might do at this point is filter this substance in order to get rid of the supernatant liquid. I'm not going to do that in this case because we're not actually going to be massing the copper 2 oxide product. If you're not going to be isolating the copper 2 oxide product, then filtering it, it seems a little bit excessive. In this case, what I'm going to do is I'm going to add water to it. And to be honest, if you were asking yourself what was the point of doing this entire reaction in this very, very large test tube, this is pretty much it. Is that by doing this reaction in this very, very large test tube, what I can do now is I can add that water, and then I can use my pipette to churn up all of this liquid in here. And at this point, all I really need to do is wait for 10 or 15 minutes. What's going to happen is that even though the copper 2 oxide's density is very, very similar to water, and it's a really, really fine particulate, it's going to have a tendency to slowly settle to the bottom anyway. And that's going to leave me with a decent amount of reasonably clear water on the top. And so then what I'm going to do is I'm just going to remove the water from the top with a pipette. I could, again, go and filter it and then try to redissolve it from the filtrate. But one of the things is that whenever you do a process like that, you always have to consider how much of the material you're going to end up leaving on the side of your glassware or in your various different pieces of filter paper and things like that. And very often going through the process of a filtration of some kind of intermediate that you're not going to isolate ends up losing more material than you would if you did something which seems less sophisticated. Which admittedly this doesn't look like it's a very complicated process. Now, if you wanted to do this in a really, really effective way, what you could do is get like a 15 or 25 milliliter tube that can fit inside of a centrifuge, and then presuming that you had another one to balance it against, if you centrifuged it, you know, all of the solid would be pushed to the bottom very, very rapidly, and then your ability to take the aqueous layer off of the top would be really, really efficient. So overall, if we put in a milliliter of 10 molar sodium hydroxide, and let's say none of it reacted, then I've diluted it out and then removed half of it, and then diluted it out again and removed half of it. So that's going to reduce the concentration to 2.5 molar. And then overall, this volume of water is itself probably 10 milliliters, 20 milliliters itself. And so that's going to reduce it by another order of magnitude. So presuming that there was no chemical reaction with the sodium hydroxide at all, this solution is now probably less than 0.1 molar in sodium hydroxide, just as a result of diluting it out with some water and then extracting about half off of the top a couple of times. And that's really all that's necessary in order to move into the next step. Our only requirement is that when we add acid, that we don't want to have so much base present in the solution already that all of the acid that we add ends up being consumed by the residual base that's left over. So we go through this process of adding a little bit of water and then taking some of the water away in order to make sure that that excess base has been removed to the extent that's convenient. Now at this point you could add just about any acid that you wanted to react with the copper 2 oxide to get the copper to go back into the solution. The original or common procedures usually call for you to add hydrochloric acid at this point for reasons I'll go into later. But we already saw hydrochloric acid at the very beginning, and we saw what the solutions with copper and hydrochloric acid looked like. So I figured that I would add a different acid. In this particular case, what I'm going to do is I'm going to add the amino acid glycine. And so I'm going to add about 1 gram of glycine to that, along with just enough distilled water to rinse that down. Now, in this case, when I say we're adding a relatively weak acid, it's a pretty weak acid, right? Glycine is an amino acid. In the form that you add it, when it gets into solution, it's going to be a zwitterion. So you're really thinking about the ammonium ion part of the amino acid as the acidic part. But the important thing about this, to me, is remembering that when we react the acid with the copper 2 oxide, that you're really thinking about this stoichiometrically. the strength of the acid is kind of irrelevant, right? It needs to be acidic because you need to be able to have that hydrogen get into the water to generate at least a little bit of hydronium ion, so the hydronium ion can react with the copper 2 oxide. But once the copper 2 oxide reacts with that hydronium ion to form copper 2 ions in solution in water, it doesn't matter, that reaction is so favorable that it doesn't matter what the strength of the acid was that you added to begin with. So then you might ask the question, well, why add glycine as an acid as opposed to sulfuric acid or acetic acid or lactic acid? And I've done all of them. The reason that I like this particular one is because it shows us another example of a change in color, a change in the absorbance of the copper ion in the presence of other things in solution. So when we did the initial oxidation and there was a very, very high concentration of chloride ion, we could see that there was a green color, right? And the green color is a result of a complex ion that's forming there. Well, here what we have is an acid, but it's also glycine, potentially a ligand. It's a chelate, so it will stick to the copper ion. And when it sticks to the copper ion in solution, the nitrogen, the amine from the amino acid, donates a lot of electrons to the copper, and that causes a color shift. And so I just think it's a really, really pretty color. If you are, like interested in dyes and paints and things like that, these are the sorts of, the things is you're looking at an example of the photoelectric effect, is that here we're very, very delicately adjusting the difference in energy between the filled and empty orbitals on that copper. And in this particular case, the way that we do that is we add nitrogen. Now, this is also not just, a game that I'm playing. Very often in this particular kind of reaction, if you put copper into solution and you were then reducing it out of solution again, some people might depend on the color of the copper to aquo complex, the blue color that copper seems to have just intrinsically. But that's not the way that most quantitative chemists recommend that you do this lab. They normally would say, well, you should run this reaction until it seems to be complete, right? You should run the reduction that we're going to do next until it seems to be complete. And then you should take out a little bit of the solution and add ammonia to it. And when you add ammonia to it, what you do is you create a complex ion of the copper and the ammonia, which has a very distinct blue color, just like this one does. I'm avoiding that, right? In this particular case, what I'm doing is by using glycine as the acid, I am making the ligand, I'm making the thing which is going to put the copper in solution, also the indicator for the presence of copper. Because there's a couple of things that are important about this particular complex that we're forming. One of them is that the color is very different from what you would expect with copper 2 ion. So as a reminder, that's sort of the copper 2 ion's color. And then as you can see here, that color shows up here where the solutions aren't very well mixed together. So this maybe is our mostly copper 2 solution. But where the glycine is getting into solution, we have this very, very vivid sort of violet purple color, right? And that's the glycinate. That's the color that's characteristic of having nitrogen, ammonia, bound to the copper ion. So one of the things is that we change the color. But the other thing is that this is a 1 molar solution of copper, and this is also less than 1 molar in concentration. So here's a 1 molar solution. Here's a solution which is less than 1 molar, but this one's a lot darker. And that gets to the second idea, which is the idea of molar absorptivity, right? This particular substance, that glycinate, just absorbs light much, much better. than the copper ion does if it just has water bound to it. And the reason that's really useful, and the reason that quantitative chemists then would recommend that before you thought your reaction was finished, you would check by adding a little bit of ammonia, is that that molar absorptivity, that increased absorbance there, tells us that we're will allow us to see very, very low concentrations of copper, in these solutions. And so that lets me know when I'm done, essentially, with this reaction. So I'm just going to stir the solution a little to make sure that everybody gets to the same point. Now, the reason that I needed to heat my reaction up has to do with kinetics, right? A weak acid like glycine is going to generate a relatively small number, relatively low concentration of hydronium ions in solution. The only way to get that to increase is going to be to increase the temperature, and then I need to increase the rate of reaction between those few hydronium ions that get generated in the copper 2 oxide surface on the little particles, and then ultimately I end up having my very, very pretty violet purple solution.